The universe began in total blackness, a silent era lasting millions of years. This was the cosmic dark ages, a time before the first starlight. We are going to uncover how the cosmic dawn broke that endless night, revealing how the first stars ignited. By the end, you will understand the precise chain of events that led from an empty void to a universe filled with light and life. How did gravity build the first stars from almost nothing? And what did those ancient giants look like when they first blazed to life? The answers trace a path directly to our own existence. What does it mean to you that we can now witness the universe's first sunrise? That initial flash of light from the cosmic microwave background was a fleeting dawn. As the universe continued its relentless expansion, that primordial glow faded into longer, invisible wavelengths, and a profound darkness reclaimed the cosmos. This was not an empty darkness, however. It was a darkness filled with substance, a vast and cold sea of neutral hydrogen gas. This gas acted like a cosmic fog, absorbing any stray packets of light and plunging the universe into its deep sleep, the cosmic dark ages. For millions of years, there were no light sources, no stars to pierce the gloom. Yet, within this seemingly uniform and stagnant fog, the universe was secretly at work. Tiny, random fluctuations in density, faint echoes from the Big Bang itself, were scattered everywhere. These minute ripples were the only game in town, and gravity was the only player. With immense patience, gravity began to pull on these slightly denser patches of gas. Imagine a tapestry woven from an almost perfectly smooth fabric, but with the tiniest, most subtle wrinkles. Over eons, gravity gently tugged on those wrinkles, gathering more and more of the primordial hydrogen. This was the quiet, slow-motion construction project that would eventually build the very first structures in existence. The entire cosmos was a silent nursery, waiting for its first newborns to stir. Those subtle wrinkles in the cosmic fabric held a profound secret. They were not truly random, but the magnified echoes of events so small they are almost impossible to comprehend. In the first fleeting moments after the Big Bang, the universe underwent a period of incredibly rapid expansion known as inflation. During this explosive growth spurt, tiny quantum fluctuations, mere ripples at the smallest possible scale, were stretched to enormous sizes and imprinted directly onto the fabric of spacetime. This left the universe with a faint blueprint of density variations, a pattern of hills and valleys in an otherwise smooth sea of matter. Without these initial imperfections, the cosmos would have remained a perfectly uniform and perfectly boring expanse of gas forever. Gravity had its instructions. It began to pull relentlessly on these slightly denser regions, drawing in more and more of the primordial hydrogen. But there was another, invisible player on the field, a mysterious substance known as dark matter. Unlike normal matter, dark matter does not interact with light at all. It simply feels gravity, and because it was unaffected by the pressure of radiation, it was able to clump together much earlier than ordinary gas. These clumps of dark matter formed vast, invisible spheres or halos that acted as gravitational anchors. Think of them as cosmic scaffolds, unseen frameworks that began to draw the hydrogen gas into their grasp. Within these dark matter cradles, the first proto-galaxies started to take shape. This was the universe's foundational work, the slow, patient gathering of ingredients in the darkness, setting the stage for the final, dramatic act of creation. How could something so diffuse and cold ever ignite into the brilliant fires of a star? Gravity's patient work was finally yielding tangible results. Deep within those invisible dark matter scaffolds, vast reservoirs of primordial gas were reaching a critical point. This was not the complex chemical soup of today's universe. It was a pure, simple blend of just hydrogen and helium, the only two elements forged in the Big Bang's furious first minutes. As these immense clouds pooled within the halos, they grew so dense that their own self-gravity began to overpower the gas's internal pressure. The great collapse had begun. Each cloud started to contract, but it was not a uniform shrinking. Like a droplet of water fragmenting as it falls, these giant clouds broke apart, their fabric tearing under the strain to form smaller, incredibly dense knots of gas. The rules of this collapse were entirely alien compared to how stars form now. In our modern universe, clouds of gas contain traces of heavier elements like carbon and oxygen, and tiny grains of dust. These ingredients act like a cosmic radiator, allowing the gas to efficiently shed heat and collapse into relatively small, stable stars. But in that ancient era, there was no dust, no heavy elements. The only way for the gas to cool was through the faint emission from hydrogen molecules, a far less effective process. This meant the gas remained hotter as it collapsed, resisting fragmentation and leading to monstrously large clumps. Each of these knots, a protostellar core, was a maelstrom of activity. As it contracted, gravitational energy converted into intense heat, causing the core's temperature to skyrocket. Conservation of angular momentum sent these infant spheres spinning faster and faster, flattening some into swirling disks. It was a violent, competitive nursery. Multiple cores would form within the same cloud, each one voraciously pulling in surrounding material, a gravitational feeding frenzy in the dark. For millions of years, these protostars were not yet true stars. They were simply spheres of gas, growing hotter and denser at their hearts, waiting for the trigger that would turn their immense weight into a sustained, universe-altering fire. Deep within that churning core, a final, critical threshold was approaching. The temperature continued its relentless climb, driven by the immense pressure of the entire cloud's weight. At the staggering mark of about 10 million degrees, something unprecedented happened. The violent collisions between hydrogen nuclei became so energetic that they overcame their natural mutual repulsion and slammed together, fusing into a new, heavier element, helium. This was the moment of nuclear fusion. A torrent of pure energy was unleashed from the core, flooding outward. For eons, gravity had ruled unchallenged, pulling everything inward. Now, for the first time, it met its match. The intense radiation pressure from the ongoing fusion reactions pushed back with equal force, creating a perfect, stable balance. The catastrophic collapse halted. A star was born. After hundreds of millions of years of absolute darkness, a new, self-sustaining source of light pierced the cosmic void. These first stars, known to astronomers as population 3 stars, were nothing like our own steady sun. They were colossal titans, thought to be hundreds of times more massive, and they burned at a ferocious, brilliant blue-white heat. Their violent birth was the true sunrise of the cosmos, the definitive start of the cosmic dawn. But their brilliant light was a double-edged sword, and the very intensity that ended the Dark Ages would soon unleash a new kind of chaos upon the infant universe. That brilliant blue-white light was a cosmic paradox. The very purity that allowed these first stars to grow so immense also sealed their spectacular fate. Made only from hydrogen and helium, they lacked the heavy elements that help stabilize smaller, longer-lived stars like our Sun. This meant their nuclear furnaces had to run at a frantic, unsustainable pace. A typical population 3 star, hundreds of times more massive than the Sun, burned through its entire fuel reserve in just a few million years. To put that into perspective, if the sun's lifetime were a full human lifespan, a population 3 stars' existence would be over in a single afternoon. Theirs was a fleeting, incandescent blaze against the eternal darkness. This furious burning produced a flood of high-energy ultraviolet radiation, a harsh and potent light that began to interact with the surrounding cosmic fog. But the most profound impact of these stellar giants was still to come, locked within their own violent deaths. They were not just beacons, they were bombs waiting to detonate, and the future chemical complexity of the entire universe depended on the explosions that would end their short lives. The violent death of these stellar giants was preordained from their first brilliant flash. Their intense ultraviolet radiation acted like a cosmic blowtorch, aimed directly at the vast sea of neutral hydrogen fog that had shrouded the universe for so long. Each photon of this high-energy light carried enough punch to violently strip electrons away from their host hydrogen atoms. This process, known as reionization, was the universe's ultimate spring cleaning. For millions of years, that neutral hydrogen had acted like a thick fog, absorbing light and keeping the cosmos in a dull twilight. Now, around every single one of those first stars, a growing bubble of ionized, transparent gas began to form. Imagine a dark landscape shrouded in a deep, impenetrable mist. Then, one by one, powerful lighthouses switch on. Each beacon doesn't just illuminate its immediate area, it actively burns the fog away, creating a clear sphere around itself. That is what the first stars were doing. These bubbles of clarity grew and grew, eventually beginning to overlap and merge. This was the Epoch of Reionization, a fundamental and universal phase change. It was the final, crucial act of the cosmic dawn. The universe was being permanently altered from the inside out, transforming from a dark, opaque realm into the brilliant, transparent cosmos we are part of today. This great illumination did more than just end the Dark Ages. It set the foundational stage for everything that was to come, creating a universe where light could finally travel freely across billions of light years, a universe we can now observe and explore. We are left with a universe transformed by fire, but one whose first heroes have long since vanished. How can we possibly know the story of stars that died billions of years before our own sun was even born? The answer lies in cosmic archaeology, a science of ghostly imprints and ancient echoes. The direct light from those first stars has been stretched by the expanding universe into the far infrared, a faint whisper beyond the reach of even our most powerful telescopes. So we must become detectives, looking for the indirect evidence they left behind. One of the most profound clues comes from studying the composition of the oldest stars in our own galaxy. Some of these ancient suns, found in the halo of the Milky Way, contain only minute traces of elements heavier than helium. They are the chemical fossils of a time just after the first stellar explosions polluted the cosmos. Their unique composition tells us they must have formed from materials seeded by that first, short-lived generation of giants. Another method is to stare as far back as we can, to the very edge of the observable universe. With observatories like the James Webb Space Telescope, we are not seeing the first stars themselves, but we are capturing the light from some of the very first galaxies. By analyzing the properties of these infant galaxies, their brightness and their rates of star formation, we can work backwards to infer the nature of the stars that must have built them. We also listen to the lingering hum of the cosmic microwave background. This ancient light carries subtle distortions, a faint polarization imprinted upon it as it traveled through the ionized bubbles created by the first stars and galaxies. It is a fossilized record of the reionization process itself. To tie all these clues together, astrophysicists run colossal computer simulations. These are not simple animations, they are virtual universes governed by the precise laws of physics. We program in the initial conditions of the Dark Ages with its dark matter scaffolds and primordial gas, and then we let gravity, hydrodynamics, and radiation take over. We watch as time and again in these digital realms, the first stars ignite as brilliant, massive blue giants, only to explode and trigger the next cosmic chapter. The simulation becomes our time machine, testing our theories against the faint fingerprints we can actually observe. It is a painstaking process of piecing together a cosmic crime scene from evidence scattered across space and time, allowing us to reconstruct a chapter of history we can never visit. While the first stars were made of blazing hydrogen and helium, their very existence depended on an invisible partner. Dark matter was the silent architect of the cosmic dawn. This mysterious substance, which does not emit, absorb, or reflect any light, interacts with the universe through gravity alone. Think of it as the hidden framework of a building, completely unseen but absolutely essential for holding up the walls and floors. In the early universe, ordinary matter was under constant pressure from radiation, which kept it from clumping together effectively. But dark matter, unaffected by this pressure, was free to collapse first. It settled into a vast cosmic web of filaments and halos long before the first star ever flickered. These dark matter structures created deep gravitational wells, invisible basins of attraction scattered throughout the cosmos. It was into these waiting basins that the primordial hydrogen and helium gas could finally flow. The gas was drawn in, pooled, and became dense enough to cool and eventually fragment into the seeds of stars. Without this pre-existing dark matter scaffolding, the gas would have remained far too diffuse, its gravity too weak to initiate a collapse. The cosmic dawn might have been delayed for billions of years, or perhaps it might never have happened at all. The very nature of this dark matter, whether it is what scientists call cold or warm, dictated the blueprint for the first structures. Cold dark matter, moving slowly, would have created a fine web of small halos, allowing stars to form in relative isolation. Slightly faster moving warm dark matter, however, would have smoothed out the smallest wrinkles, potentially leading to fewer but more massive first stars. So every time we look up at the night sky, we are seeing the legacy of something we cannot see, a hidden component that wrote the first and most important chapter in the story of light. That final, brilliant flash of a population 3 star was not the end of its story, but the start of its true purpose. When these colossal giants could no longer support themselves against their own immense gravity, their cores collapsed in a cataclysm of unimaginable force. The resulting supernova explosions were events of a scale we can scarcely comprehend, far more energetic than most stellar deaths we observe in the modern universe. These were not mere outbursts, they were total annihilations, blasting the entire star apart and scattering its guts across the cosmos. Within the furious heart of these explosions, under extreme temperatures and pressures, a new chapter of cosmic chemistry was being written. For the first time ever, atomic nuclei were fused together to create elements heavier than helium. Carbon, the backbone of life, oxygen, the breath of animals, and even iron, the strength of our world, were forged in these fleeting, violent moments. The pristine universe of pure hydrogen and helium was gone forever, polluted with the seeds of complexity. This enrichment of the cosmic gas clouds was a total game changer. That first generation of stars had lived and died in a sterile environment, but the clouds that coalesced after their destruction were fundamentally different. They now contained traces of these new heavy elements, which scientists collectively call metals. Even a tiny amount of this stardust acted as a powerful coolant, allowing the gas to shed heat far more efficiently as it collapsed. This meant that gravity could now form smaller, denser clumps of gas. The result was a second generation of stars, known as population 2 stars. These stars were smaller, more stable, and could burn for billions of years rather than just a few million. Their longevity was crucial as it provided the stable environments necessary for the next great leap. Around these longer-lived stars, the enriched gas could also coalesce into rocky planets, no longer just gaseous giants. The violent death of the first stars was the single most important act of cosmic recycling. Their explosive ends were the crucibles that forged the raw materials for everything to come, from the smallest rocky world to the most complex life forms. Their brilliant births lit up the darkness, but it was their spectacular deaths that gave the universe its future. These first stellar titans were not lonely beacons in an empty void. They were social creatures, born into crowded stellar nurseries deep within the first proto-galaxies. Picture not the grand, sweeping spiral of the Milky Way, but a faint, dwarf galaxy, a mere speck containing only about 1/1,000,000th of the mass of our own home galaxy. Within these small, dense crucibles of gas and dark matter, the first stars ignited in clusters, their collective light and fury creating a chaotic and violent environment. This was the next great organizational leap of the cosmos, the transition from individual stars to entire stellar systems. Gravity's work was far from over. It continued to pull on these infant galaxies, drawing them toward one another in a slow cosmic dance. Over hundreds of millions of years, these small building blocks began to merge, their stars and gas mingling to form larger, more massive structures. Each collision was a construction project on a galactic scale, a fundamental step in building the majestic galaxies we recognize today. The environment inside these primeval galaxies was unimaginably intense. The relentless ultraviolet glare from dozens of massive blue stars bombarded the surrounding gas, while supernova explosions rocked the cosmos every few million years. These blasts carved out vast cavities and sent powerful shock waves rippling through the remaining hydrogen, compressing some regions to trigger new star birth while violently dispersing others. It was a continuous feedback loop of creation and destruction, a forge where the very rules of galactic life were being written. Studying these infant systems is like looking at the blueprints for a cathedral. By observing the oldest, most distant galaxies with tools like the James Webb Space Telescope, we are essentially seeing those blueprints in action. We can watch how stellar radiation and supernova shocks dictate where new stars can form and how a galaxy grows from the inside out. This journey from a single, brilliant star to a coordinated system of millions of them marks a pivotal turn in the story of our universe. It was the moment when chaos began to give way to a new, higher level of order, setting the stage for an even grander architectural project, the weaving of the cosmic web itself. That chaotic forge of the first galaxies was just the beginning of a much grander design. The universe was not merely creating isolated islands of light, it was weaving an entire cosmic tapestry. This pattern is known as the cosmic web, the largest structure in existence. It is a vast, interconnected network of galaxy-filled filaments, immense clusters at the intersections, and staggeringly empty voids in between. This entire architecture can be traced back to those tiny density ripples from the universe's infancy, the very same wrinkles that gravity used to build the first stars. Over billions of years, gravity acted as a master sculptor, relentlessly pulling matter from the voids and feeding it into the filaments and nodes. The first stars and galaxies did not ignite randomly. They sparked to life along these dark matter filaments, tracing out the invisible skeleton of the cosmos like glitter sprinkled along the strands of a vast, three-dimensional spiderweb. Where these filaments crossed at the nodes of the Webb, matter piled up into the deepest gravitational wells. These became the sites of immense galaxy clusters, cities of thousands of galaxies bound together by their collective gravity. The emptiness of the voids is just as telling. These are not mere gaps, but regions where gravity lost the tug of war, where the initial density was too low for structures to form, leaving behind cosmic deserts spanning hundreds of millions of light years. How do we possibly see this structure we are inside of? Astronomers create maps not of land and sea, but of the universe itself. By using powerful telescopes to painstakingly plot the positions and distances of millions of galaxies, a pattern emerges. Each galaxy is a single point of data, but when viewed in 3 dimensions, they clearly outline the filaments, nodes, and voids of the cosmic web. This grand architecture was not built after the fact. Its blueprint was drawn in the first instant of time, and the events of the cosmic dawn were the moment that blueprint first became visible, when light finally began to trace the hidden contours of creation. This single, simple fact about cooling determined the entire scale of the first stars. For a cloud of gas to collapse under its own gravity, it must find a way to lose energy to cool down. Think of it like this: a hot gas has high internal pressure, it pushes outward and resists being squeezed. Only by cooling can the gas lose that pressure and allow gravity to win, pulling everything inward to form a star. In our modern universe, this process is incredibly efficient. Clouds of gas are filled with tiny dust grains and complex molecules like carbon monoxide. These act like a car's radiator, allowing the gas to efficiently shed heat and collapse into relatively small, stable stars like our Sun. But the first gas clouds were pristine. They contained no dust, no carbon, no oxygen, nothing but hydrogen and helium. In this sterile environment, the only available coolant was a fragile molecule, molecular hydrogen. This is simply 2 hydrogen atoms bonded together, but molecular hydrogen is a terribly inefficient coolant. It can only shed heat through very specific, low-energy vibrations, a slow and clumsy process compared to the modern cosmic toolkit. This inefficiency created a fundamental barrier. A cloud could not start collapsing until it had gathered enough mass for its gravity to overpower the internal heat pressure that the weak hydrogen coolant could not remove. The cloud had to be massive enough to simply muscle through the problem. This is the core reason why the first stars are theorized to have been such behemoths. The physics of a metal-free universe demanded giants. It was a cosmic catch-22, where the very purity of the ingredients forced the first stellar creations to be both brilliant and brief, setting a dramatic and unique stage for everything that followed. This search for the first stars leads us to an unexpected place, our own galactic neighborhood. We cannot see those original giants directly, but we can find their children. The oldest stars in the Milky Way, known as population 2 stars, are the immediate descendants of that first generation. They formed from the ashes of the very first supernova, from gas clouds that had been only lightly sprinkled with newly forged heavy elements. Finding one of these ancient stars is like finding a living fossil, a relic from a time just after the cosmic dawn. Their importance lies in their chemical purity. A star with extremely low metallicity, meaning it contains only the faintest traces of elements heavier than helium, is a cosmic time capsule. Its atmosphere is a preserved record, a chemical snapshot of the cloud from which it formed billions of years ago. By analyzing the specific elements present in that atmosphere, astronomers can perform a kind of forensic investigation. They can work backwards to determine what kind of star must have exploded to create that particular chemical signature. Was it a single, colossal supernova, or perhaps the combined fallout from several? did it explode with a certain energy, spinning out specific ratios of carbon to iron. These ancient stars tell that story. Massive surveys like the Sloan Digital Sky Survey have scanned the heavens, identifying a precious handful of these ultra-metal-poor stars. Each one is a rare and invaluable data point. Their light, analyzed by powerful spectrographs, is not just a beacon, it is a page from a history book written in the language of elements. It is our most direct, albeit still indirect, line of evidence back to the universe's first, brilliant, and doomed generation of stars. Our ultimate time machine is now in orbit. The James Webb Space Telescope represents a fundamental shift in our quest to witness the cosmic dawn. Unlike the Hubble Space Telescope, which primarily sees invisible light, Webb was specifically designed as an infrared observatory. This is the key to looking back in time. The light from the very first stars and galaxies has been traveling for over 13 billion years. The expansion of the universe has stretched this ancient light, shifting it from the visible part of the spectrum all the way into the infrared. Webb's giant golden mirror and its suite of supercooled instruments are built to catch this faint, redshifted glow. It is like having a new kind of vision, allowing us to see the heat signature of creation itself. With this powerful tool, astronomers are not simply looking for the individual first stars, which are still too faint and small to see at such distances. Instead, they are hunting for their collective signature in the earliest galaxies. They search for the unique chemical fingerprint of a galaxy still dominated by population 3 stars, a system that has not yet been polluted by the heavy elements from later supernova. They probe the timeline of reionization by studying how the light from the most distant galaxies has been filtered by the intervening hydrogen fog. The early results have been startling. Webb has discovered a surprising number of very bright, very massive galaxies that existed only a few 100 million years after the Big Bang. Their existence so early in cosmic history is challenging our models of how quickly galaxies could assemble. Were the first stars even more efficient at forming than we thought? Did dark matter clump in ways we did not predict? Each new image is not just a pretty picture, it is a data set that forces us to question, refine, and sometimes completely rethink the story of how our universe woke up. We are no longer just piecing together theories from indirect clues. We are now staring directly at the nursery walls of the cosmos, watching as the first lights flicker on across the newborn universe. These supercomputer simulations are more than just complex animations. They are entire digital universes born from pure mathematics and physics. Cosmologists start by programming in the initial conditions of the cosmos, those faint density ripples from the Big Bang, along with the precise amounts of dark matter and primordial gas. Then they set the rules, the fundamental laws of gravity, hydrodynamics, and radiation. With a click, they set time in motion and simply watch what unfolds over millions of virtual years. The result is a cosmic time lapse, a dynamic narrative that shows dark matter weaving its invisible web first. We see the gas flowing into those gravitational scaffolds, pooling and swirling until the conditions are just right. Then, in the heart of a virtual proto-galaxy, a point of light erupts, a simulated population 3 star igniting for the very first time. These models allow scientists to run countless experiments. What happens if dark matter is slightly warmer or colder? Do stars form in glorious isolation, or do they ignite in frantic, competitive clusters? How does the blistering ultraviolet radiation from one massive star blow away the gas around its neighbors, shutting down star formation in a process called feedback? The simulation becomes a laboratory for testing the entire story of the cosmic dawn. Yet every simulation is an approximation, a necessary simplification of a universe of near infinite complexity. The true power emerges when we compare these digital creations to real observational data. When the James Webb Space Telescope sends back images of an unexpectedly bright early galaxy, scientists immediately rush to their simulations. Can their models produce such a massive galaxy so quickly after the Big Bang? If not, what physics are we missing? This constant dialogue, this tension between prediction and observation, is how our understanding evolves. Each new piece of data is a key, and each simulation is a lock, and together they are slowly unlocking the deepest secrets of our cosmic origin story. So the universe did not wake up all at once. This cosmic dawn was not a single dramatic sunrise, but more like the slow arrival of a misty morning, where light emerges in patches across a vast landscape. The evidence points to a universe that flickered to life unevenly, with the first stars igniting in isolated pockets millions of light years apart. In one region of the cosmos, a massive dark matter halo would gather enough gas to trigger that first brilliant flash. A bubble of intense ultraviolet light and ionized gas would burst into existence around it, carving out a small sphere of clarity in the universal fog. Meanwhile, in another, still dark region, the slow-motion collapse of gas was only just beginning, with millions of years yet to pass before its own first star was born. The initial phase of this great illumination was therefore incredibly patchy. The cosmos was a tapestry of light and shadow, with brilliant islands of transparency adrift in a sea of lingering darkness. Over time, as more stars formed and more galaxies assembled, these individual bubbles began to grow. They expanded into the surrounding darkness, and crucially, they started to merge with neighboring bubbles. The isolated neighborhoods of light began to connect, forming ever larger regions of a transparent universe. This was a process that could not be rushed. Current estimates suggest the entire transition, from the very first star to the completion of reionization, spanned several 100 million years. That is an almost unimaginable length of time, yet in cosmic terms, it was a remarkably swift and transformative phase. The timeline of this event is not just a matter of historical curiosity. It acts as a critical stopwatch for astrophysicists. The speed at which reionization occurred tells us directly about the nature of the sources that powered it. If the process was very rapid, it would imply an overwhelming number of incredibly bright, energetic objects, like quasars or vast numbers of massive stars. A more gradual and extended timeline, however, points toward a dominant role for these first stars and small, early galaxies. By meticulously mapping the end stages of this process with telescopes, scientists can work backwards to estimate just how many of those first stellar giants must have existed and how brightly they must have burned. The pace of the dawn reveals the character of the dawn's architects. The most colossal of those first stars may have met an even more dramatic fate. For the true giants, those weighing in at over 260 times the mass of our Sun, a supernova was not the end. Their gravity was so overwhelmingly powerful that when their fuel ran out, no outward force could possibly resist the final, catastrophic collapse. The entire star would have imploded, vanishing from the visible universe and leaving behind only an infinitely dense point in space, a primordial black hole. These were not the stellar mass black holes we find today, formed from stars rich in heavy elements. They were the first of their kind, the universe's original portals of no return, born from the purest, most massive stars that ever existed. Their emergence created a new and permanent kind of structure in the cosmos, a gravitational anchor point that could persist for billions of years. One of the most compelling theories in modern cosmology suggests these primordial black holes did not just sit in silence. They may have acted as seeds, the foundational kernels for the supermassive black holes that now lurk at the hearts of nearly every large galaxy, including our own Milky Way. How does a black hole grow so immense by feasting? A newly formed black hole would have begun its life surrounded by the dense gas of its host proto-galaxy. Its immense gravity would have drawn that gas inward, creating a swirling, superheated accretion disk that shone with the brilliance of 1,000 galaxies. As it consumed this material, the black hole would have grown in mass and power, potentially merging with other primordial black holes in a series of cosmic collisions. This relentless growth could have allowed these seeds to balloon into the billion solar mass behemoths we observe in the early universe, far sooner than our models once thought possible. The very existence of such ancient supermassive black holes is a clue pointing back to this violent seeding process, but not all of these first black holes needed to become giants. Some could have wandered the early cosmos as solitary gravitational ghosts. Their pure gravitational influence, without any accompanying light, would have subtly shaped the gas clouds around them, potentially triggering new star formation or disrupting infant proto-galaxies. We cannot see them directly, but we might be able to hear them. When two such black holes spiral inward and merge, they shake the very fabric of spacetime, sending out ripples known as gravitational waves. Observatories like LIGO and Virgo are now detecting these waves from black hole mergers across the universe. It is possible that some of these signals are the echoes of events from the cosmic dawn, the final, inaudible screams of the first stars as they collapsed into darkness, their legacy written not in light but in the subtle stretching of space itself. That stardust connection is more than just a poetic phrase. It is a physical fact written into our very cells. Every atom of oxygen that fills your lungs with air was not present at the beginning of the universe. It was missing. The Big Bang produced only the lightest elements, hydrogen and helium, with a trace of lithium. For nearly every other element on the periodic table, the birthplace was the heart of a star. The iron that carries oxygen in your blood was forged in the final moments of a massive star's life, just before it exploded. The calcium that strengthens your bones was fused in that same stellar inferno and then blasted into space. Even the carbon, the fundamental scaffolding of all known life, was created through the relentless nuclear fusion that powers stars like our Sun. But that chain of creation had to start somewhere. The first stars were the pioneers of this cosmic chemistry. Their immense cores acted as the universe's first nuclear reactors, taking the pristine hydrogen and helium from the Big Bang and performing the first act of cosmic alchemy. They fused hydrogen into helium, and then, in their later stages, they began to fuse helium into carbon and oxygen. This was the universe's first step toward complexity. These pioneering stars did not live long enough to create the full suite of elements. They could not forge the iron for blood or the silicon for rock. But they did not need to. Their crucial role was to break the pristine monotony of the cosmos. By seeding the void with that first carbon and oxygen, they fundamentally changed the properties of the cosmic gas. When these stars died in their spectacular supernova, they enriched the surrounding clouds with these new, heavier elements. The next generation of stars then formed from this slightly polluted material. Those second-generation stars now had carbon and oxygen in their cores, allowing them to fuse even heavier elements in a cascade of increasing complexity. Each stellar generation built upon the work of the last, with massive stars creating heavier elements and then dispersing them through supernova or through slower stellar winds. The material that eventually coalesced to form our solar system, our Earth, and our own bodies had been cycled through multiple generations of stars. This means the oxygen you are breathing right now was likely forged in several different stars across the history of the Milky Way before it found its way to you. You are not just made of stardust, you are made of the collective legacy of countless stars, a heritage that began with that very first brilliant generation. This realization ties our own biological narrative directly to the cosmic dawn. The same physical processes that lit up the darkness also forged the raw ingredients for planets, oceans, and life itself. Our existence is a direct continuation of that first sunrise, a living testament to the universe's journey from simple darkness to complex light. This faint radio whisper from neutral hydrogen offers a completely different way to see the cosmic dawn. It all comes down to a tiny, fundamental shift inside the simplest atom in the universe. Deep within every hydrogen atom, the electron and the proton each have a property known as spin. Think of them as tiny magnets that can either point in the same direction or in opposite directions. When these spins flip from being aligned to being opposed, the atom releases a very specific amount of energy, a single photon with a precise wavelength of 21 centimeters. This falls squarely in the radio part of the spectrum. For most of cosmic history, this subtle transition was happening constantly throughout the vast sea of neutral hydrogen gas. That means the Dark Ages and the cosmic dawn were actually filled with a pervasive, faint radio hum, a signature written in the spin of countless atoms. The key is that the expansion of the universe stretches this signal, just like it stretches light. By tuning our radio telescopes to different wavelengths, we are effectively tuning into different cosmic times. A signal received at a longer wavelength comes from further back in time. If we can map the 21-centimeter signal across a wide range of redshifts, we are not taking a single snapshot. We are creating a three-dimensional movie of the universe's most important transition. We could watch, frame by frame, as the first stars and galaxies ignite, and their radiation begins to carve ionized bubbles into the neutral fog, tracing the progress of reionization across hundreds of millions of years. This is the grand promise driving a new generation of radio telescopes, like the Hydrogen Epoch of Reionization Array, or HERA, a silent forest of antenna dishes in the South African desert, and the Future Square Kilometer Array, a colossal international project that will span 2 continents. These are not optical telescopes looking for points of light. They are radio ears listening for a background chorus, a signal that is incredibly faint and buried under a cacophony of modern radio interference from our own civilization and even our own galaxy. Separating this cosmic static from the noise is one of the most formidable data challenges in all of science. Success would mean more than just confirming our theories. It would reveal the temperature of the primordial gas, telling us when the first starlight began to heat the cosmos. It would show us the precise geometry of the reionization bubbles, revealing whether the first stars were lonely giants or social clusters. This faint spin flip of hydrogen is a direct recording of the universe's awakening, and we are now building the machines to play it back. Another invisible force was likely at work in those first stellar nurseries, a subtle presence woven into the fabric of the collapsing gas. We are talking about magnetic fields. The question of their origin is a deep cosmic mystery. Were these fields primordial, woven into the universe from its very first moments, or were they born from the chaotic dynamos of the first stars and galaxies themselves? Most theories suggest it began with incredibly weak seed fields, faint traces of magnetism that were then dramatically amplified. As the primordial gas collapsed and swirled in turbulent motions during the formation of the first stars, it could have acted like a natural generator. This churning motion, a process known as a dynamo, would have stretched and twisted these weak seed fields, winding them up into powerful, organized magnetic forces. This newly forged magnetism was not a passive bystander. It could have profoundly influenced the very architecture of star birth. Magnetic fields create tension, a kind of cosmic rubber band that resists twisting and compression. In a collapsing gas cloud, this magnetic pressure could have helped support the cloud against its own gravity, influencing how it fragmented. Did it prevent a cloud from breaking into smaller pieces, leading to fewer but more massive stars? Or did it channel the flow of gas, guiding material into flattened disks or even powering the first colossal jets that shot out from the infant stellar systems? These fields would have introduced a new layer of physics to the cosmic dawn, a set of rules that governed how energy and momentum were transported through the chaotic gas. Their presence is crucial to understand because magnetic fields are the silent architects of modern star formation. In today's universe, we see them shaping nebulae, controlling the rate at which gas can collapse into stars, and launching the spectacular jets from young stellar objects. If we want to truly recreate the physical conditions of that first epoch, we must account for this magnetic dimension. Pinpointing the origin and early strength of these fields is not just an academic exercise. It is about discovering whether the universe's first structures were built with a full toolbox, or if they had to invent the tools as they went along. This search for primordial magnetism is another vital piece of the puzzle, a force that may have gently guided the hands of gravity itself. Yet the James Webb Space Telescope is just our first real step into this ancient past. To truly see those first stars directly, we need to build even more powerful eyes, observatories designed from the ground up for this single, monumental task. Concepts are already on the drawing board for a new generation of space telescopes. One such vision is the Habitable Worlds Observatory, a mission that, while focused on finding Earth-like planets, would carry a coronagraph so advanced it could block the glare of distant stars, potentially revealing the faint, clustered light of the first stellar populations. Another concept is a dedicated large far-infrared telescope, an instrument specifically tuned to the deeply redshifted light of the cosmic dawn, light that has been stretched far beyond what Webb can easily see. On the ground, the era of the extremely large telescope is dawning. These are colossal structures like the 30-meter telescope and the extremely large telescope, with primary mirrors spanning over 30 meters across. They will gather immense amounts of light and employ sophisticated adaptive optics systems, using laser guide stars to constantly measure and correct for the blurring effects of Earth's atmosphere in real time. This will provide an incredibly sharp, deep view into the infrared sky, allowing us to probe the earliest galaxies with a clarity we have never before possessed. But perhaps the most ambitious proposals look beyond Earth entirely. The far side of the Moon offers a unique and pristine environment for astronomy. Shielded from the constant radio chatter of our planet and free from an obscuring atmosphere, it is the ultimate quiet zone. A giant radio telescope built in a lunar crater could listen with perfect clarity for the 21-centimeter signal from the neutral hydrogen of the Dark Ages, mapping the universe before the first stars. An optical telescope placed there would have an unobstructed, eternally dark sky, providing a vantage point unlike any other. Each of these proposed missions represents a leap in our technological ambition, a direct continuation of the human drive to witness our own origins. The march of technology is relentless, and with each new generation of instruments, we are not just building better telescopes, we are building better time machines, bringing the moment of that first, brilliant sunrise into ever sharper focus. This fine-tuning of the cosmos goes far beyond a simple historical curiosity. Every link in the chain we have followed, from the exact strength of gravity to the specific density of dark matter, appears precisely calibrated. If the force of gravity were even slightly weaker, those initial density fluctuations would have been too feeble to gather gas into stars. If dark matter did not exist in its particular, mysterious form, there would have been no cosmic scaffolds to draw in the primordial hydrogen. The universe would have remained a cold, dark, and permanent void. The fact that these constants hold the exact values they do is what allowed the cosmic dawn to proceed, which in turn led to galaxies, planets, and ultimately to us. This observation brings us to a profound and somewhat haunting question. Why does the universe seem so perfectly set up for the emergence of life? This line of thinking is known as the Anthropic Principle. It is not a scientific theory with predictive power, but rather a philosophical lens. It suggests that the universe we are able to observe must, by necessity, have properties that allow for the existence of observers. We are here to question the cosmos because the cosmos was built in a way that permits our existence. It is a self-selecting reality. You could think of it like a cosmic lottery. If the fundamental constants of nature were randomly dialed, most possible universes would be stillborn or sterile. We, however, find ourselves in the one universe where the numbers came up just right, the single ticket that produced a cosmic dawn, stellar factories, and conscious life. This does not answer why the constants are what they are, but it frames our entire cosmic story in a startling new light. The journey from the first star to your ability to hear this story was not a random accident, but a narrative that had to unfold in this one very specific way. The cosmic dawn was not just a chapter in a history book. It was the necessary first step in a chain of events that makes our own questioning presence possible. This dynamic of creation and destruction defined the very first galactic ecosystems. A newborn population 3-star did not simply shine, it actively rewrote the rules of its own neighborhood. Its blistering ultraviolet radiation did more than just ionize hydrogen. It poured immense heat into the surrounding gas. This heating raised the gas pressure dramatically, creating a powerful outward force that resisted further gravitational collapse. In the vicinity of these stellar giants, the cold, dense pockets of gas necessary to birth new stars were simply vaporized away. The first stars erected invisible barriers around themselves, carving out vast territories where no other star could form. But their influence did not stop with radiation. These massive stars also unleashed ferocious winds, torrents of charged particles streaming from their surfaces at millions of kilometers per hour. These winds acted like cosmic sandblasters, relentlessly pushing against the nursery's remaining gas. Then came the final, most dramatic act, the supernova. The explosion did not just enrich, it evacuated. It blasted the majority of the surrounding gas clear out of the proto-galaxy, dispersing it into the intergalactic void and effectively shutting down star formation for millions of years. This violent feedback was a form of cosmic self-regulation. By dispersing and heating the raw fuel for new stars, the first generation placed a hard limit on its own population. Yet, in their destructive fury, they also sowed the seeds for future creation. The expanding shock waves from their supernova could travel for light years, eventually slamming into distant, quiescent clouds of hydrogen. This sudden compression was like a hammer blow, triggering instabilities and collapse in regions that might have otherwise remained dormant for eons. The same event that quenched star formation in one area could ignite it in another. This intricate feedback loop meant the first stars were both architects and wrecking balls. They dictated the rhythm and location of the next wave of star formation, ensuring their own short-lived dynasty would be followed by a more diverse and stable stellar population. Their legacy was not just the light they emitted, but the very structure of the galaxies they built and then fundamentally transformed. Establishing a precise timeline for the cosmic dawn is like carbon dating the entire universe. Current evidence, primarily from the Planck satellite's detailed map of the cosmic microwave background, suggests the first stars flickered on between 200 and 400 million years after the Big Bang. This was the true ignition. The subsequent Epoch of Reionization, that great clearing of the cosmic fog, is thought to have unfolded over the next several hundred million years, largely complete by the time the universe reached its 1 billionth birthday. This chronology is not just a list of dates, it is a direct measurement of the universe's creative engine. A rapid dawn implies incredibly efficient, powerful star formation, while a more gradual awakening points to a slower, more methodical buildup. Yet this established timeline is now being rigorously tested. The James Webb Space Telescope is peering back to previously inaccessible eras and finding a surprising number of bright, massive galaxies that existed shockingly early. Some of these galactic structures appear to have assembled far sooner than our models predicted, suggesting the first stars may have ignited even earlier, or that they formed with a ferocious efficiency we do not yet fully understand. Each new data point from Webb is another tick of the cosmic clock, forcing us to recalibrate our understanding of how quickly darkness gave way to light. Refining this chronology is the ultimate goal, as it tells us not just when it happened, but precisely how the universe's first great transformation unfolded. But were they all giants? The dominant image of the first stars as colossal, short-lived titans may not be the full picture. Advanced computer simulations reveal a more nuanced reality. It appears the initial mass of a star was exquisitely sensitive to its local environment. In a perfectly smooth, quiet cloud of primordial gas, the physics indeed favored the formation of massive behemoths. Yet the early universe was far from quiet. It was a place of immense turbulence, with gas flowing along the dark matter filaments in chaotic, swirling currents. This turbulence could have caused a collapsing cloud to fragment into a wider range of clumps, some large and some small. Furthermore, a background of radiation from the hot, young universe could have subtly influenced the cooling process, altering the final outcome. These factors open the door to a fascinating possibility. While the first generation was surely dominated by massive stars, it might have also included a minority of smaller, more modest stars. These would have been true cosmic relics, population 3 stars with masses similar to, or even less than, our own Sun. The implications are staggering. A star with a mass like the Sun, born from pure hydrogen and helium, would still be shining today. Its nuclear furnace would have burned so slowly and steadily that it could have survived for the entire 13.8 billion year history of the universe. This means one of the very first stars ever born could be hiding in plain sight, a fossil star quietly orbiting in the halo of our own Milky Way galaxy. Finding such an object would be the ultimate discovery, like finding a living dinosaur. It would provide a direct, untouched sample of the universe's original composition, a pristine laboratory for testing every single one of our theories about the cosmic dawn. This search for a low-mass first star is already underway. Astronomers are using massive sky surveys to hunt for the most chemically primitive stars imaginable, those with metal content so low they are virtually undetectable. Each candidate is scrutinized, its light broken down into a spectrum to search for the telltale signature of a pure, unenriched composition. The Holy Grail would be a star with absolutely zero metals, a true first-generation survivor. The fact that we have not yet found one suggests they are incredibly rare if they exist at all. This ongoing search forces us to confront a fundamental question about the initial mass function of the first stars. Was it a narrow distribution producing only a specific type of massive star, or was it a broad spectrum, creating a diverse first family of stellar sizes? The answer defines the character of the cosmic dawn, determining whether it was illuminated solely by brief, brilliant flashes, or also punctuated by the enduring, gentle glow of smaller, eternal lights. To grasp the origin of those first stellar giants, we must rewind the cosmic clock to a moment almost beyond comprehension. A tiny fraction of a second after the Big Bang, the entire universe underwent a growth spurt of unimaginable ferocity, a period known as cosmic inflation. In less than a blink of an eye, the cosmos expanded at an exponential rate, becoming trillions of times larger. This violent stretching did something profound to the very fabric of reality. It took the faint, ghostly ripples of quantum fluctuations, the inherent jitteriness of empty space at the smallest scales, and magnified them to a cosmic size. These microscopic wrinkles were imprinted onto the newborn universe as the first variations in density. They were the universe's very first blueprint, a pattern of hills and valleys in an otherwise perfectly smooth sea of energy. The character of these seeds was dictated by the properties of a mysterious entity known as the inflattened field, the driving force behind this explosive expansion. The specific way this field evolved and decayed determined everything about the initial conditions, setting the amplitude and distribution of those all-important density ripples. How can we possibly see the imprint of such an ancient event? The answer is written in the oldest light we can observe. The cosmic microwave background is a fossilized snapshot of the universe just 380,000 years after the Big Bang. The tiny temperature variations mapped across this afterglow are the direct descendants of those primordial quantum fluctuations, magnified by inflation. When we look at that speckled map of the infant cosmos, we are essentially seeing the amplified quantum noise from the first instant of time. This means the grand cosmic web of galaxies, the majestic swirls of stars, and the very existence of our own sun can all be traced back to the quantum mechanics of that inflationary epoch. The story of the cosmic dawn is not just a tale of gravity and gas. It is the ultimate consequence of a beautiful and fundamental connection, a direct lineage from the smallest quantum tremor to the largest structures of light. Ultimately, the story of the cosmic dawn is a stress test for our entire understanding of the cosmos. This is not merely about filling in a blank page in a history book. It is about verifying the very rules we believe the universe operates by. Our leading cosmological framework, known as the Lambda cold dark matter model, makes specific, testable predictions about how structures should have formed from those initial quantum ripples. The ignition of the first stars and the assembly of the first galaxies represent a critical benchmark for this model. If our theories are correct, they must accurately forecast when this dawn broke and how those first structures looked. If the real universe, as seen through the eyes of the James Webb Space Telescope, shows us something different, something unexpected, then we are forced to confront a thrilling possibility. Our model, for all its success, might be incomplete. The properties of dark matter itself might need a revision. Our grasp of dark energy, the force accelerating cosmic expansion, might be flawed. Or, most profound of all, our understanding of gravity itself might require adjustment in these most extreme environments. The data now arriving from the edge of time is putting the Lambda cold dark matter model through its most rigorous exam. Every surprisingly bright early galaxy, every unexpectedly massive black hole, is a question posed directly to our fundamental physics. In this way, the cosmic dawn is more than a chapter of ancient history. It is an active laboratory, a cosmic particle accelerator on the grandest possible scale, where the mysteries of the first light hold the key to a deeper, truer comprehension of everything. This ancient story of first light touches something deep within the human spirit. It is more than a cosmic timeline. It is a fundamental narrative of emergence. We see a universe that began in the simplest possible state, a formless sea of darkness, and through its own intrinsic laws, it gave birth to light and eventually to the breathtaking complexity that allows us to exist. This journey from nothing to something, from darkness to light, echoes our own human stories of creation and discovery. It connects to our most profound questions. Where did we come from? Are we alone? The cosmic dawn provides a scientific, evidence-based answer to the first question that is, in its own way, as majestic as any myth. We learn that our home, the Earth, is not the center of a static universe, but a tiny, recent arrival in a cosmos that has been evolving for billions of years. This knowledge is profoundly humbling. It shrinks our world to a speck, yet simultaneously elevates our presence. We are the universe become self-aware, a way for the cosmos to look back on itself and understand its own origins. The fact that we can deduce the story of the first stars using only mathematics and the faint light collected by our telescopes is a staggering achievement. It is a testament to the power of human curiosity and reason, our relentless drive to push back the boundaries of the unknown. This understanding does not just belong to scientists. It inspires artists to capture the birth of galaxies on canvas. It moves philosophers to ponder our role in this grand scheme, and it invites every one of us to look up at the night sky with a new sense of connection. We are not separate from the cosmos. We are a living, breathing part of its continuing story, a story that began with the first flickers of light in an unimaginable void. Even with all we have uncovered, the cosmic dawn remains shrouded in profound mysteries. We have pieced together a compelling narrative, yet many of its fundamental details are still hotly debated. What was the true nature of those first stellar giants? We speak of them as colossal behemoths, but did they all share a similar, massive scale? Or did the first stellar nurseries produce a wider family of stars, including some smaller, longer-lived siblings that might still be shining today? The efficiency of their formation is another open question. How quickly and readily did gravity sculpt those pristine clouds into shining beacons? The surprising brightness of the earliest galaxies spotted by the James Webb Space Telescope suggests that star formation might have been a far more vigorous and efficient process than our best simulations predicted. This forces us to reconsider the entire environment of the early universe. Were the first black holes mere byproducts of the first stellar deaths, or were they active architects from the very beginning? Their precise role in shaping the infant cosmos is still unclear. Did they act as seeds for the supermassive black holes we see today, growing at a frantic pace that defies our current understanding? And what of the dark matter itself? We see its gravitational influence everywhere, but the identity of the particle remains one of the greatest unsolved problems in all of physics. Is it cold, warm, or something else entirely? Its fundamental properties dictated the very blueprint for the first structures, and until we pin it down, a crucial piece of the cosmic dawn puzzle will be missing. Each new discovery from our telescopes and simulations does not simply provide an answer. It often peels back a layer to reveal a new, more intricate set of questions beneath. This is not a sign of failure, but a testament to the dynamic and living nature of this scientific quest. The collaboration between theoretical predictions, immense computer models, and revolutionary observational data creates a powerful feedback loop, a cycle of discovery that propels us forward. The journey to witness the universe's first sunrise is far from over. The next decade, with even more powerful observatories on the horizon, promises to challenge our assumptions once more, bringing the dawn into a focus we can scarcely imagine today. Our journey through the cosmic dawn brings us face to face with a profound truth. The universe awoke from its long dark slumber, not with a single command, but through a magnificent, patient chain of events. We have witnessed gravity's slow sculpting of the primordial gas, the breathtaking flash of the first nuclear fires, and the great clearing of the cosmic fog during reionization. This was not a random sequence, but the universe's first great act of creation, setting into motion the entire cosmic evolution that would eventually lead to galaxies, planets, and to us. The search for understanding is far from over. It is propelled by the incredible power of new telescopes and the brilliant virtual universes of our computer simulations. Every new observation, every refined model, adds another crucial piece to this grand and beautiful puzzle. So the next time you find yourself looking up at the night sky, remember that you are witnessing the legacy of those first magnificent stars. Every point of light you see and the very atoms you are made of owe their existence to that initial dawn, whose brilliant fires broke the eternal darkness and made our own story possible. This narrative of the cosmic dawn is, in the most fundamental sense, our own origin story, written in the language of the stars. We would love to hear your thoughts on this incredible cosmic journey in the comments. And if you want to explore more mysteries of the universe, be sure to subscribe.